So here we have the graph of a world population. And you can see that along the x-axis we have our years. Those are given as 1800, 1850, 1900, 1950, and 2000. So those are just years that are given there. Now, one thing we might do instead of putting these large numbers in for x is we can set our x values back and let this first one be x equals 0. And this would be 50 years later. This would be 100 years later. This would be 150 years later. And this would be 200 years after we initially started. And it turns out that this actually works better in terms of writing a model instead of having those large values for the years. And it also helps us because when we draw a true linear model, if x is 0, then our first point will be here on the y-axis, and then we can go up like this. This is a bar graph, but we're really going to look at this in terms of a line. So I'm going to let x be 0, and x is the number of years after 1800. So at the initial x of 0, we're talking about the year 1800. This x of 50 would mean 50 years later, 1850, 1900, 1950, and 2000. Now I'm going to write in my y values 0.959, and this is in billions, so that's going to actually be 959 million, 1.22 billion, 1.62 billion, 2.52 billion, and then 6.08 billion. And if we were to look at this in terms of a line, I think it's pretty easy to see that if we were to make a line here, our model would miss a lot of the points that are in between. However, let's go ahead and do this as a line, and then we're going to do it as a different kind of model and talk about why that model is probably a better fit. So once again, I'm going to enter these values in the calculator by pressing Stat and then 1 for my list. If there are numbers in the calculator, I can simply make sure that my cursor is on the number. Let's say there was a number here, and I just put the cursor there and hit the delete key to clear that out. My x's are 0, 50, 100, 150, and 200. And my y values are 0.959, 1.22, 1.62, 2.52, and 6.08. Again, I'm going to use the calculator's feature of being able to write. Again, I'll use the calculator. It has a feature where I can write or predict a model based on the data. So to do that, Stat, Calc, so I arrowed over. And again, I'm going to pick the linear regression, or the line of best fit. And here we have y equals ax plus b, where our slope, or a, is 0.02079, and our b value, or y-intercept, is 0.7749. Now, depending on what the instructions of the problem says, you may be allowed to round, and I'm going to actually write this model as y equals 0.021x. I'm going to round the 0.0207 to 3 decimal places, and I'm going to round my b to 3 decimal places, 0.775, so that I get a model for this data of, as predicted by the calculator for me, y equals 0.021x plus 0.775. And now we might look and see how well this model makes a prediction, let's say, for example, for the 1900s. So 1800 was the first one, 1850 was the second one, 1900 is our third data point here. Now I'm going to find out what the model predicts. And so I need to substitute x is 100 and then add the 0.775. Multiply this by 100. I'm going to get 2.1 plus 0.775. And if you add those together, you're going to get 2.875. Now look at this model and look where this model actually predicts. It predicts it somewhere almost to 3. So you can see in this case this model is off fairly significantly. So we want to keep this linear model in mind, but we want to look at another kind of model, and then we'll come back to this and we'll talk about how that model is going to work better than a linear model in the case where the rate of change is so different. And I can look at this graph and I can see that the rate of change is significantly different, even without doing the subtraction in my y values here. My x's are all constant. They're all going up by 50. But look at the difference in the y's. This bar to the top of this bar changes by a little bit. From here to here changes by more. From here to here, the y changes are even larger. But look at this last one. Wow, we had a huge jump in that last one. So that vertical change is increasing. The amount it changes by is getting larger and larger. And that tells us that there's probably a better kind of model that we should be using. And in the case of this, we have what is called an exponential function. So let's look at a couple of examples. An exponential function where we have a rate of change that increases, but at an increasing rate. So I'll pick a few values for x, and then I'll pick a few values for y. And so I need to get all the way up to 32 on the y-axis. So I'll go by 10 on the y-axis, 10, 20, 30, 40, 50. But I'll leave my x scale at 1. And I'll take a look at the graph. At 0, it's about 4. At 1, it's about 8. At 2, it's up to 16. At 3, we're all the way up here at 32. And it's a little hard to see with this scale, but what's happening here is very similar to what we saw with our world population, and that is that these points don't lie on a perfectly straight line. They really lie more along a curve, and in this case it's a curve of what we call an exponential function. So look at what's happening to your rate of change, or your change in the y's in particular here. We go up by 2, then by 4, then by 8, then by 16. So we are increasing at an increasing rate. So it's going uphill from left to right, but it's going to rise faster and faster the farther we go along the x. We could have a similar situation, but it might be decreasing at a decreasing rate. So we might have something like x is 1, 2, 3, 4, 5, 200, 100, 50, 25, 12.5. In this case, you will see that the values are dropping. The rate of change, we're going down by 100 from 200 to 100. And again, this is over 1. So each time I didn't mention the change in the x, but our denominator was just 1 in each case. Same thing here. X is going up by 1. But look at what's happening to the y. Down by 100, down by 50, down by 25, down by 12.5. So our delta y, delta x, or our slope here, is not a constant. It's changing. But it is a negative, which means it's falling from left to right. And if I were to graph this, I would see that it is falling very rapidly at first, down by 50 whole points, the first one, and then down by 25. So over time, it's dropping, but not by as much. So we would call this decreasing at a decreasing rate. So just draw a little sketch here real fast of these guys. We started out at 200. Started out at 200, and then we were all the way down to 100, and then we were down to 50, and then we were down to 12.5, and then we would be down even more. And if we draw this in again, you don't have a straight line, you have more of a curve, and this is actually called an exponential function. So when you have a function that's either increasing at an increasing rate or decreasing at a decreasing rate, the model is actually better described as an exponential model. So I want to go back to this world population example, and I want to change my model over from linear to exponential and see if we can get a better idea of what's going on here. And now I want to leave all this linear stuff because we're going to go back and use the new model to predict and see if we can get closer for the 100th year, whereas we were pretty far off before, from 1.62 million to 2.875 million. That's a pretty significant difference in our model value. So let's go back and do this model using what's called exponential regression. And you'll notice that in my data set here, I still have the same values I had a few minutes ago. This time, though, I'm going to use a different model. I'm going to use the exponential instead of linear. So I'm going to press Stat, go over to Calc, and you can see the list here, and this arrow beside the number 7 actually means that there are other values. So I'm going to arrow down. And it turns out that if I go all the way down, the 10th one listed here as a 0 is the exponential regression. So I'm going to do the exponential regression on this data set, and I get a completely different model that I need to know how to write. Again, I'm going to round. Again, we have an A value and a B value. And I'm going to round to 3 decimal places. Notice what the model says. Y equals A times B to the X power. This is what makes this an exponential function, and that is that our X, or our value that's changing, is going to be in an exponent. So taking what we were given, that this time, instead of mx plus b, the linear model, we have an exponential model, a times b to the x, where our a value rounded is 1.055 times, and I like to use the parentheses for multiplication, 1.008 to the x. Model looks totally different here because it is actually an exponential model. Now let's go back to the calculator and find out what the answer would be here if we were finding y at 100. Remember, we found y at 100 previously, and it predicted a 2.875. We saw that was way up here and not anywhere near the actual data point of 1.62. So let's take a look at this model and see what we get. And I'm going to use the calculator because these numbers can get kind of messy. So I'm going to have 1.055 times, and the calculator recognizes times with the parentheses, 1.008, close my parentheses, exponent key is the caret key, raised to the 100. So again, I'm not using the exact model here, I've rounded, but I'm going to get a prediction here of 2.34. Again, our model is not exact. It's actually still off fairly significantly, it seems, but it is still closer to the actual value of 1.62. The linear predicted a 2.875 and the exponential predicted a 2.34, and since this one is closer to the actual, that is the actual value of 1.62, we say that this model is a better model for the data, at least for that point, that third point there in the data set. So what's really important here is that you recognize how to read these models from the calculator and then go back and use each model to compare what you would get using that model to see which one of them is a better model for the actual data. Now here we have a situation we haven't seen before. This graph to the right shows the average weekly DVD rentals for a store in a small town for various years from 1995 to 2010. You will notice in this case something slightly different is happening than what we've seen before. And what you see here is that you have an increase followed by a decrease. And in this case, we'll have an even different kind of model than the two we've seen so far. Remember, so far we've seen linear, and we saw that linear works best when you have a rate of change that is constant or very close to constant. That is, the points along the graph are changing at about the same rate. And then we saw exponential, and we saw the case of the world population, and we saw that as we changed, that instead of having a straight line, that it was more of a curve upward. And then we actually saw one that showed that it could actually be downward, just like your linear function could go down from left to right, so can your exponential. But in the case of this particular situation, we have a data set where you have an increase followed by a decrease. So I'm going to let x equals 0 correspond to 1995. And then every 3 years will be my other years, 1998, 2001, 2004, etc. So we'll start with 0, then we'll go up by 3 years. And I believe I'm going to need another row to my table. And we can put in our y values: 350, 410, 580, 631, 573, and 421. And if you look at this rate of change, you will notice that it starts out by increasing at an increasing rate, in fact. So it goes up by 60, then it goes up by 170, then it slows down a little bit, up by 51. These are all ups, but then it drops. It starts to fall. So we have, and these are all constants, up by 3s here. So we have a rate of change that is not a constant. At first, it's a positive slope, if you will, positive rate of change. It's going up first, reaches a peak, and then it starts to come back down. So it wouldn't make sense to put a linear function here, because a linear function continues in the same pattern over time. And the exponential model similarly continues to increase, so that's not going to be a good model. So we need a third type of function or model to help us describe what's going on in this case. Now we'll come back to this one, but let's just look at a couple of examples first. What we actually have here is something that's going to be close to what is called a quadratic function. And you may have seen or heard of a parabola before. And the reason a parabola is going to describe this better than that line or exponential curve is that we're going to have a minimum or a maximum value, and that's what happens with a parabola. A parabola is a U shape that will have either a minimum or maximum value. In the case of the parabola that opens up, we have what's called a minimum. And a parabola that opens down, we have what's called a maximum. And that's actually the point on the curve that you may have seen or heard referred to as the vertex. And so when you have that peak or valley, that peak at the top or valley down low, a parabola or a quadratic function is going to be better in terms of describing your data. So let's just look at a couple of quick models here. Here is a set of data for our parabola. I'm going to use a scale of 2 on the y-axis and a scale of 6 on the x-axis and a scale of 6 on the y-axis. And I don't have a lot of points to show this, but the first one shows you that it comes down, then it turns around and goes back up. And actually, if we were to look on this other side, it would come down from the left and up on the right. This is called a parabola. And in this case, that parabola minimum happens to be at the origin 0, 0. So that's going to describe data that falls at first, but then rises or decreases, followed by an increase. Now, you can have the same sort of situation with a parabola where you have an increase followed by a decrease. So an increase to a maximum followed by a decrease. Just want to give you kind of a general idea. We don't even need to plot any points. But just know that when you have the situation where it's going up originally, increasing, reaching a maximum value at some point and then falling, then your data is better described by a quadratic than by a linear or an exponential. So here's our situation. I'm going to use the calculator once again to help us find our function. So I'm going to delete any information I had previously just by putting my cursor and hitting this delete key, and then enter the values that I have: 0, 3, 6, 9, and 12. And my y values that were given: 350, 410, 580, 631, 573, and 421. So in this situation, and of course I need that last x value to be 15. So for every y you have to have an x, for every x you have to have a y. And so in this situation where I see I have a peak that is rising to a peak and then falling, I can still use the calculator to help me, but when I go over to calc, I'm going to select number 5 for quadratic regression. And in this case, it gives me a quadratic equation: y equals ax squared plus bx plus c, and it gives me the values that I need to use for a, b, and c in this quadratic function. And I'm going to round, this time I'm going to round to 2 decimal places to find my quadratic function. So that's going to be negative 3.91 x squared plus 67.21 x plus 312.86. So my quadratic model, ax squared plus bx plus c, and I just use those values the calculator found for me: negative 3.91 x squared plus 67.21 x plus 312.86. That's going to be a quadratic model that will model this data. And I'm going to go back to the calculator and show you how when I graph this, it will fit our data points. Now this is what my data points would look like if I were to scatter plot those data points. You can just sketch those by hand also. But if you're curious to know how I did this, I go to my window and I set my window to make sure that my x's, which went from 0 to 15, will fit on my graph. And so I set my x's from negative 10 to 20. Then I set my scale to be at 1, and that's fine. That means how many tick marks. Then I set my y minimum to be negative 10, and since it went all the way up to 631 on the y table, I just picked 1,000 for my y maximum. And I didn't change my scale, which means you can't see any tick marks here, so I'm going to change that scale to 100, and that's going to make my tick marks, make my graph look a little bit better. When I draw the graph, here's my data set. Now, how well does our curve fit that? Well, I'm going to type in the y equals the curve that we got. So negative 3.91 x squared plus 67.21 x plus 312.86. And when I draw the graph again, look how my curve fits into those points. So if I'd use a line or an exponential, those kinds of functions continue either rising or falling. But if I need a curve that rises to a point and then falls, I need a parabola. And you can see that this parabola fits this data pretty well. Now there's one last situation we need to talk about, because you're going to run across some problems of this type. And that's the case where you have data that is increasing but at a decreasing rate. So we're seeing here our trend is to go up, but it's slowing down in terms of how fast it's going up. So each of the bars is rising, but they're not rising by as much each time. And in this case, we have what is called a logarithmic function. Now, there are a couple of kinds of logs that you're going to run across, and those logs are going to be listed as either log or ln. So we don't spend a lot of time in this particular course worrying so much about the properties of logarithms and exactly what is a logarithm. But let me just give you a little background so you'll kind of understand when you see these in equations or in functions what they mean. When you have a logarithm, log, you're looking for the exponent that a base 10 is raised to. And I'll explain that in just a couple of minutes by giving you an example. When you have a logarithm that is an ln log, that's actually, ln is for natural log or natural logarithm. And in that case, the base is e, and e is called the natural base. And when we're dealing with e, all you really need to know at this point is that it's approximately 2.72. And so you probably know that you've been told over time to know that pi is an approximate value of 3.14. Well, in this case, just know that e is an approximate value of 2.72. Not exact, but it's very close to 2.72. Now, let's talk about what these logarithms actually mean. I'm going to give you an example. Log of 100. If you were to do this in your calculator, it would come out to be the value 2. And that goes back to what power you raise a base of 10 to get 100. Well, in this case, the value would be 2. So a logarithmic function is actually describing an exponent that is needed to get a particular value. And where you have this base of 10, this is actually called a common logarithm. Versus a few minutes ago, we saw the base e called a natural logarithm. This is called a common logarithm. Let's do another common log. Log, you may see it in all caps on your calculator, but it can also be written like this. Log of 1,000. That's asking us, what power do we raise a base of 10 to get 1,000? Well, that would be 10 to the third. Now, logarithms don't always come out to be these nice whole numbers. I might be asked to find the log of 50. And that means 10 to what power comes out to 50? Well, 10 to the 1 is 10, and 10 to the 2 is 100. So if we want to know the exponent that will come out to 50, it's got to be somewhere between 1 and 2. That's how I would write somewhere between 1 and 2. Well, this is where my calculator comes in handy, because I don't know how to do this in my head. So I can open up my calculator and I can press the log key, 50, and I can see that it's between 1 and 2. It's about 1.69897. So if you want to check this, 10 raised to 1.69897 is very, very, very close to 50. Now, it's not exact because I rounded, but you can see that 49.9999995 will round to 50. So that is what a logarithm actually is. And you will see these represented in some equations. Now, pay attention to whether you are using the common log, log, or the natural log, ln. Which one is used is actually just going to depend on the actual situation of the problem that you're solving.